Welcome to another testing video from the Ultralight Airplane Workshop. In this video, we're going to continue a little series we've been doing on nose ribs that could go onto the UWS-4 ultralight airplane. Now, as I mentioned in the last video, in this video, I'm going to design a cantilever style rib and see how it works. See how light it can make it, see how much load it can carry. Now, I've been asked in a previous video in this series, why would I want to do a cantilever nose rib if I can make the truss style rib lighter? In this case, I wanted to see what kind of design could I do, how much load could it handle, how much would it weigh, and then I would compare that to a truss style rib. Now for a cantilever style rib, what I'm talking about is a rib that has a shape kind of like this, where you've got suction up here on the top pulling up, and you've got pressure on the bottom pushing up. But up here at this very nose, it's not carrying much load, so all the load is being carried here, and these are acting like beams that are held cantilever style back here where we attach to the spar. So it's basically two cantilevers. This one does not carry as much load as this one, so this one could be designed differently. In a previous video, I was asked why I was doing the testing that I was doing for preparing for the nose rib design. In other words, testing these angles here, putting a weight out here, testing in this compression, where it'd be compression down in here, or in this orientation, putting a weight on here and testing this in tension. That's because once I know what these various radiuses and flange widths can do, then it'll give me a better idea of how to design this portion of the rib in order to make this cantilever strong enough. In other words, this area right in here like this. And so that's what I did here. This is the design I did for the cantilever rib. So I used 3-inch radiuses in here, which is what I determined I needed when I was in compression. In other words, down here on this corner, when this was in compression, which means I could have made this radius probably smaller because this is in tension and it can handle more load. When I did my test, if I remember right, when I was in tension, I could carry about 50, well, it was more than 54 pounds. It didn't fail on me, so it was somewhere over that. Down here, I can only carry about 20 pounds because in compression, and in compression, you're usually weaker. But those two together would be about 74 pounds. That would be my 3.8 G load on this rib. Now, of course, I need to go over that. I have a safety factor of 1.4, which is up around 112 pounds or so. So I really didn't have a lot of hope that this would work. Although I was hoping that the sum of the parts would be a little more than individuals. Now, I also knew that since these were cantilever and this is acting like a beam here, and since I was using the same aluminum thickness all throughout here, as the load comes back this direction, this moment arm gets more and more, which means this web had to carry more load. So I made this thicker as it came out here towards the spar. Now, I didn't do any calculations to figure out how much thicker it had to be. I just kind of took a guess at it. Which brings up another thing I was asked about is, why not use some finite element analysis or finite element method to do some preliminary testing inside the computer before I actually build something? And that's actually a good idea, and I've seriously thought about it, but I really wanted to get out here and get in the shop and actually build something. So that's why I went this route. Oh, and by the way, I should mention, this is actually a form that I used to bend the inner flange. This is a 70-degree bevel, I believe, and that's to take care of the bounce back or rebound. Whenever you bend fairly hard in aluminum, 60-61, it's going to want to bounce back. And so I hit it with the mallet to get it down to this 70 degrees, but it's going to bounce back to about 45, which is what I wanted. So that worked out pretty good. And this is what the template looks like after it's been cut out. I got some registration holes. I got about a 1/2-inch flange width in here. This is meant to attach to the spar. And then there's a flange on the top and a flange on the bottom. And I put a little bit of extra out here to bend over to hold the shape of the nose when the skin is wrapped around it. I'm not sure I'll keep doing that. I may actually cut off this very sharpest curve up here. I don't think I really need that. And then to bend the outer flange, the top and bottom flange, I use this. So again, it's got the 70-degree bevel on here. And then this back edge where we attach to the spar. Now in that case, I bent it the other direction. Instead of bending it this way, I bent it up. And that's to make it easier to access the rivets that go in through here. With this flange bend in the same direction as this inner flange, the inner flange would be interfering with getting access to use a pop rivet gun to access these rivets that attach to the spar. So I bent it the other direction. I figured that would work, but it does offset the load that's being carried from the rib over to the side about 1/4 of an inch or so. But I didn't think that would be an issue, so I decided to go ahead and give that a try and see what would happen. So I wanted to give this a full test, a reasonable test. So I wanted to put a rib into something that was like the spar and the wing skin that I was going to eventually use. Now in a previous video, I figured out that I should probably put some of these rivets closer together because of the failure mode that I had when I was in tension. So when weight was being pulled down here, I was getting a failure down here on this bottom flange. It was buckling and then allowing things to collapse. And that was when I was using 3-inch spacing. So I've gone to roughly a 2-inch spacing, minimum spacing, because that worked out pretty well when I did another test. Now I do know what the load is along this wing. In a previous video I talked about doing chord-wise load estimation. And I'll put a link up in the upper left-hand corner that you can take a look at if you haven't seen that before to figure out how to do the load along the chord. So then I changed my rivet spacing depending on how much load each rivet would have on it. In another video that I did earlier, when I was doing some rivet pull testing, I wanted to see how much force it would take to deform the rivet hole in 20 thousandths thick aluminum and 16 thousandths thick aluminum. At that point, I wanted to put in as few rivets as I could, so I was thinking about using a 3-inch spacing. That put a 20-pound load maximum on a rivet up here at the nose if I did that. And that would be using 20 thousandths thick aluminum. But since I've changed my rivet spacing down to 2 inches, that changes the load per rivet, it reduces it, which means I can go back to 16 thousandths aluminum. So that's what I did here in this rib. Instead of using 20 thousandths, I've switched to 16 thousandths because closer rivet spacing. And since we're talking about rivets, the reason I wanted the rivets is I'm going to put a wing skin on here. It's about a 12-inch wide wing skin, roughly. I was thinking on the Univis 4 I'd probably have about 14 inches between ribs. So it kind of represent the span along the wing that any rib would take of 12, 14 inches. It also helped me doing testing because I could lay things on top of it a little bit easier. And then I made a fairly realistic spar. So I used 1 inch by 1 inch angle aluminum, 1/8 of an inch thick on the top and the bottom. I made that spar the same width, the 12 inches that I was going to make the wing skin. And then I used 20 thousandths thick aluminum web as a solid web, no lightning holes, as the shear web on that spar. And in fact, you can see that over here. So here's lower spar. Actually, it's upside down. I'll talk about that in a moment. So this is actually the upper spar. This is the bottom spar. This is a stiffener. This is also Z-shaped, so I can get access to the rivets. And I've riveted the rib with 1-inch spacing here. And I riveted the web with 1-inch spacing. I don't think I probably need that much, but I did overkill because I wasn't really testing the spar here. I'm testing the rib. I did roughly 2-inch spacing on the rivets, but from the skin into the spar caps. And then I put these braces on here to help hold this system while I'm doing the testing, because I'm putting a lot of weight here. And speaking of weight, let's talk about how I'm putting the load on this rib. So here's a side view of our rib. Now you may be able to tell that this rib is upside down. When we're in flight, the force is going to be in this direction, the main force. And so what I'm doing is I'm taking advantage of gravity to give me that same force. So I had to turn the rib upside down. So this is the bottom of the rib, this is the top of the rib. And again, here's the spar and the nose. Now I've mentioned before, I know how much load is going to be on each rivet along here in the rib, on both the bottom and the top. Now I can tell you right now, I didn't put as much load up here. I call this the top, this is actually bottom. I didn't put quite as much load here on the bottom as I should have, as it's going to be on flight. But that was just because I was starting to have a little bit of trouble with my skin bending down, and so I ended up putting that extra load down here on the bottom. And let's talk about the load. So as you can probably guess, this is a whole bunch of rebar that I've sawn up into chunks. I did not bother measuring the length to get a certain weight. All I did was cut it up into convenient sizes, and I'd weigh individual ones and put on a piece of masking tape how many ounces there were on each bar. So I've got some like this. I've got little short ones. So the long ones are from about 13 ounces up to almost a pound, 16 ounces. And then I got a bunch of little ones too. Oh, as you can tell, the way I put them on here on the bottom is I hung them using twine. And then as you can tell, I have these 5-pound blocks I put on here also just because I had those hanging around. The way I attached them is I put these little brackets over each rivet. And then I put holes in these brackets. So there are 4 rivets per bracket, and I have a little hanging hook here, and I hang the twine on the hook. And so that lets me put a certain load on each rivet along here. This rib has been sitting with this load on it for more than a week now. And this load is at 1.5 times the expected maximum load at 3.8 Gs. And that's well, right now it has 116 pounds on it. It's about 112 for the maximum load. And although it hasn't completely failed, and by the way, since it didn't fail, we're not going to have any time lapse of me putting the weight on here because it really isn't that interesting. But it is starting to fail. It's had some buckling issues. So let me show that to you. So let's start at the back, and it's probably going to be hard to see, but right back here, this is actually bowed this direction. Not a whole lot, but it has bowed a little bit. Now let's come down here. You can see that the skin is bowed down. Now this bottom skin is in compression. And so it's starting to get some bow down here, and I'm starting to get bow in between each of the rivets. That's kind of to be expected. Now here's the first interesting failure, which is right here. You can see this kink right here. So it's gone that direction, and it's kinked. So let's come up here to the nose. Now this is quite a bit deformed. When I first had this set up, the skin was pretty much touching the rib all the way around. Well, this rib right here is now pinched. You can see that little point right there. This is pinched down a little bit. So this weight on top has caused this to collapse a little bit. So to make this stronger, this really should have a little bit more curvature in it. If I'm going to stick with this cantilever design. And working our way back, it's in pretty good shape up here until you get to right here. Now this is bent, but this time it's bending towards us here. A little bit of a bend right here, so that's starting to collapse. So we had a buckle right here too. So it hasn't completely failed yet, but it's on its way. Well, now what I'm interested in is finding out how bad the permanent deformations is. In particular, I want to see how much the rivet holes have been deformed, how much they've been elongated, how much the rivet's trying to pull through the holes. Now, I imagine that most of these buckles that we just looked at, particularly this bottom skin and back here at the spar, those aren't permanent. They'll come back. Some of these others may not come back after load is taken off. We'll see. But something to keep in mind is the Part 23 regulations, at least the old ones, said that any permanent buckling or permanent deformation that happens after you get to your load limit, in this case 3.8 Gs, is okay. You don't want to have a complete failure though. And below the 3.8 Gs, at least for this airplane is what I'm using is 3.8 Gs, you don't want to have any permanent deformation. So I'm going to tear this apart and we're going to see what we get. Well, I've removed the weights, and I thought before I tear it apart, I'd show you a little bit more. I'd show you that the deformations, some of them are still there. So we got permanent deformations, and I want to give you a little better idea of how the hanging mechanism worked for the weights. So let's take a look at what I did here for holding the weights on here. So on the top, I didn't do anything until I got back here till about the 5th rivet. And then I put a little flange here to help hold the weight where we're starting to get a little bit of a downturn. And then here, there's another one to hold some more weight about the 6th rivet. So it helps keep that weight from sliding off here at this steeper angle. Now let's look at the bottom side so you can get a better idea of how I did the hanging. There are 10 rivets under here, and you can see I've got these little bent flanges I put on here. There are 4 rivets for each one of these. And then I've got a hook that I put in there, and then a string that goes down to weight. So that's how I put weight all along here on the bottom. Now let's look at the deformations. So this one back here at the back, it's gone. There's no more bend there. The skin is no longer bent here, which is what's really the top. It's on the bottom here. And then on the rib itself, this little kink, that's still there. That's a permanent deformation. Up here on the nose, right there, that is a permanent deformation. And then back here on this one, that one's still deformed. So with a little bit of change in design, this rib could probably be made to handle even the load factor of 1.5, 112 pounds without permanent deformation. So up here at this web, I could make this one a little bit longer. I can make this one a little bit wider, maybe a 1/2 inch or so. I could actually remove some from down here. This is stronger than it needs to be. So maybe remove maybe 3/8 of an inch, maybe 1/2 an inch, bring it down a little bit. Might need to add just a little bit up in here, and then also here at the nose, add some width here. And so this rib could probably even then handle an even greater load. Or since this rib was perfectly fine at the 75-pound load at 3.8 Gs, I could probably just leave all the rest of it about the same, but just remove this part down here, about 1/2 inch here. So I can make this rib a little bit lighter, and it would still carry the required load. So I got the rib removed. I still have the permanent deformations. So you can probably see one here. This one on the nose is, yeah, it's still there. And then this one here is still there. But what I'm very pleased about, oh, you know what? There is still just a slight bend here. I'm a little surprised about that. Now that could have happened in forming, but I don't think so. I think we got a permanent bend right here. What about the straightener? Stiffener does not have a permanent bend in it, although I made it out of 20 thousandths thick aluminum instead of 16. So it might be worthwhile to make this flange here just a little bit deeper. Although probably not necessary, because I don't think the permanent deformation happened until we started to get up to the high loads, when we're up in the safety factor area. But one thing I'm very pleased with, there are no permanent deformations of any of the drill holes where we had rivets going through. So that's fantastic. I'm very pleased about that. It looks like maybe this flange might be permanently deflected up just a little bit, maybe. Hard to be sure. I think it might be, because I think I had all these at 90 degrees. So this one may have bent up permanent. These others look like they're pretty straight, except for possibly this one. And these are all good. By the way, all these little bends in here, that is to help this flange bend to the contour as I was forming the rib. So these are intentional. So for the most part, I'm pretty darn happy with this design, even though some of it was intentional, like these 3-degree radiuses and making the flange thicker as it came back here to the root, so it acts like a beam. But how much to do that, how far to extend it up forward, that was all a guess. So I clearly guessed wrong up here. I didn't think there would hardly be any bending force up here. I figured that these 2 beams would take all the effort, but I think once this one buckled, that put a lot more force up here and caused this one to buckle. So it's possible just widening this flange here would take care of that issue. And I wrote down how much the weight was on this. This was 72.5 grams. So making about the same rib, just a few changes. I think it could be even stronger, but it's not really necessary. Like I said, at the 75-pound weight, we're at 3.8 Gs. I didn't see any deformations at all. It looked great. But I'm not yet happy. I want to see if I can make a lighter rib, but not cantilever. I don't think I can really go much lighter than this and have this be successful. So in the next video, we're going to try a shape a lot like this. So this is a truss style, where this is a truss. So basically on this one, I'll probably do something similar to what that is. I'll probably have a vertical right in here, probably about right in here. There'll be a vertical piece of aluminum and then an angled piece coming down here. So when we have the load pulling up on this wing, this piece will be in tension. This will be in compression. So I'll have to make sure that this can handle the compression load. And then the nose, I'll probably just put a fill in here. And I think that can handle transferring the nose load back here. Now there will be load pressing, let's see, pulling up here and pushing up here. I'm going to make these much thinner since they're not cantilevered. This is basically supported here and here. So since it's supported on two ends, it's no longer a cantilever beam. It's an end supported beam, so I can make this thinner. Same thing up here. This will be a beam that's supported on two ends, so I can make this thinner here. Now the question is, how thin can I make it and still have it work? Well guys, that's it for this video. I'm pretty darn happy with this rib design. Just a few minor improvements and I think it'll be perfectly fine. But we're going to compare the weight of this one to what I can get with something like this. Guys, thanks for watching. Till next time.